A very good afternoon. Welcome to the Bose Colloquium of today, and which will be given by Dr. Tata Narasingha Rao, uh, who is, we actually call him as Tata. And I always knew him as Tata. I didn't know he has all this big thing after Tata, but now I know that. So Dr. Tata received his PhD degree in chemistry from BHU in 1994. And after working at IIT Madras as research associate, he moved to University of Tokyo. That's where he learned eating fish, in 1996 as a JSPS postdoctoral fellow, and subsequently became lecturer also in the Tokyo University in 2001. And he joined International Advanced Research Center for Powder Metallurgy and New Materials, which is known popularly as ARCI with this acronym, in Hyderabad in 2003 as senior scientist. And as already announced, currently he is the director of ARCI. And in addition, he is also an adjunct professor at IIT Hyderabad. He is recipient of several awards and honors that include the MRSI Medal in 2009, Tokyo University Science President Award in 2014, and Academician of Asia Pacific Academy of Materials Award in 2015, Technology Day National Award, which is actually given by President of India in 2016. And he also has gotten the MRSI annual prize, which is one of the highest recognition of MRSI. And as suggested by the title of the talk he is going to deliver, he is known for his translational research. Primarily, his group is focused on materials development by novel synthesis processes, particularly for lithium-ion battery, namely the lithium iron phosphate and lithium titanium titanate. And the novelty is huge level of mass level of production. And these will be transferred to the industry. I mean, some has been already transferred to the Indian industry, and others are in process of technology transfer, even including the international technology market. And I think Tata's visit to SN Bose Center is very, very important, given the fact that SN Bose Center hosts one of the 5 different TRC. And recently, we had an evaluation meeting of TRC where it was suggested, and I think that was a very, very pertinent suggestion, that we should all 5 TRC in close collaboration, and networking between these 5 TRC is very essential. They are really the technology people, because they have been working with this culture and knows this culture very well. On the other hand, we are like, a little child who has started how to stand, starting from the crawling stage, because we are basic scientists, but who are making a move to this domain. And when you make a move to a new domain, like a child, perhaps it's much more helpful if someone holds your hand when you are trying to stand up. So in that context, I think this visit is extremely important. And along with Dr. Tata, two of his colleagues, it's really nice and kind of them. They have also agreed to visit us. And Dr. Bharadwaj will give the talk tomorrow. He is here, and anyone interested, and he is the chief of their technology cell. So if anyone is interested to know more details about it, you feel free to interact with him. He will anyway give a talk tomorrow at 11:30. And we also have Dr. Prabhu, who is from the ARCI, but their Chennai office, and who is a person more to do with materials, magnetic materials, energy materials, and with the expertise on rare earth magnet. So, and making this material. And we do have synthesis people who will be interested to interact with you. And I think this is just a beginning, and I do hope that this interaction will continue. So with that, I welcome Dr. Tata to deliver his seminar.
This you switch off. Leather pointer is there.
Can you please switch off the light?
Thank you. Is it too loud?
It's okay.
Yeah. Thank you so much, Professor Kanishki, for giving me this opportunity to visit this lab for the first time. Before I'm retiring tomorrow is my last person as director at DRCA. So I thought I should come here as director so that I receive a warm welcome. Otherwise, if I come day after tomorrow, maybe no one will be there. And I have to hire people like politicians. Then it's nice hospitality, and I should also thank my colleagues to come here, who will be helpful for some of the topics what we have common interest. Then, as Darshi said, we are translation materials. We are all inorganic materials specialists. And then, if you see ARCA, we have cocktail of disciplines like we have chemistry, physics, and chemical engineering, mechanical engineering, metallurgy. So the name metallurgy itself, but metallurgy is required for a lot of even chemical translation materials. I will give you of the case studies also. And some people say International Advanced Research Center, it should be IARC, ARCI. I say the Doctor of Philosophy, not the PhD, it's a PhD. All big things are not there, should be put us without that. Right? So ARC is like that. Then the mandate from DST is translation of laboratory research in technology and transfer to industry. So the performance parameters of ARCA is seen as, of course, obligations, MOU when we sign with DST. We keep low score for the publications, but reasonable score for the patents, and then high score for the technology transfer and extra model funding. These are some of the 5 major ones where we have to show our performance, and we are quite successful in that. So the title I put, Crossing the Valley of Death. So the Valley of Death is a very different, it's not my word, it is a word well known in any kind of business models that when you take low TR level, that is what you do at the lab stage, lab level, to do the proof of concept. And then beyond that, if you want to go to a validation at the larger scale, then it's not so easy. So I keep giving the example of my wife making chutney. For 3 of our people, me, my wife, and my son, she makes brinjal chutney because we are vegetarians so well, and no one, I never understand what she puts in it. I said that you tell me the recipe, we'll file a patent. And then she's excited. She said, okay, my wife is my colleague. She actually does details of the badness and all, but she also makes chutneys. So, but I say that we can file patent of this recipe provided you can make this chutney for 50 or 100 people with the same taste. Then she says, she will make another instead of brinjal, she will make another vegetable chutney because that is much easier to make multiple chutneys because only 3 people. But one chutney to take the mass scale is more engineering. To take, for example, if you want to make chutney in small one, you take A, B, C, and then put it and then grind it. And then, but if you want to do it 50 liters or 10 kgs level, then you cannot have a big one. It's not a linear scale. You cannot grind it, and even Salman Khan cannot do that. You need to have engineered designs with fluid dynamics calculations, and which we don't do. So what we do, we tie up with, at that stage, we tie up with the reactor engineering guys, some companies, and then give all our inputs, and then they make the reactors, and then we keep modifying so that we get. So that is what is required. So this is called Valley of Death. If he doesn't succeed in making this chutney for 100 people, then no one cares, and then we are at loss. So that's scare. That's why it's called Valley of Death. You can make multiple chutneys and publish papers multiple numbers, which is very important anyway. But one chutney to take to that level, crossing the valley, that is not so easy. But if you go to other countries like Japan, even China, and they focus on crossing the Valley of Death because they want to make money. you want to make business, right? So my next slide shows this. The value of that. It is a laboratory research which is called invention. What we do, you publish paper, or if it is worthwhile to go for, if you think that can be translated, then go for a patent. And once you cross this, then successful commercialization launch, that is called innovation, where you can think of transferring the know-how and then making the money. I'll give you an example of lithium iron phosphate, what Tanushree was telling, and then how we made money starting from a small scale. So this is quite challenging, but it is important if you want to realize the self-reliance and make in India and so on. So just to say what ARCA can do, Adi Channel 1 mission, we have a role to play there. We have one of the mirrors in this VELC, that is visible emission line chronograph. And one of the mirrors, this M3 mirror, this one here, where your light is coming and then it is being focused on the secondary metallic mirrors. But once it is focused, it's like a sun. You have a disc light and then you have a, it's like that. The disc light is so, which we don't want, because what is to be analyzed is the coronal light. So this disc light has to go out, so you have a hole of the mirror, and then this mirror should have the high temperature, high thermal current, so that through these legs it should be dissipated so that your machine will not be damaged. So this is what we did, and then this mirror we made, and then this is what is transferred, and it is polished by Leos in Bangalore, and then it is already it's now in orbit, it's going on. So the lightweight, a lot of powder metallurgy, how to make silicon carbide is a high temperature material, how to make it and then dense it and make it dense component, then lightweighting with the 5-axis CNC machine, and then again heaping, and a lot of things are important involved. And then it took almost 7 to 9 years to go to this. Now we can make bigger mirrors also. So here we work for the civilian sector, and then we also work with the automotive, and we also work for strategic sectors. ISRO is our close partner, and then defense is our close partner too. And recently we have started a new project where we already established a huge facility, pilot facility to make low expansion glass ceramic for the space mirror application. ISRO, if you go to the BSS, they have a huge piled up zero expansion glass mirrors which are imported from Germany. Now they want self-reliance. So we have established this facility. Of course, the facility is German, but you have to make these numbers in big numbers, and then it has to be polished, and then it should be foolproof that it is near zero expansion. What you do is you make is glass ceramic. You make the glass material which expands, and then you ceramize in a controlled way where you have nanoparticle lithium silicate, and then that should lithium aluminum silicate, and that will contract while the glass expands. You have to mass number, what is that, volume fraction, and then weight fraction. All this should be compensated within glass and dense number. So this is the process control what we make, and then these are all being now established at ARCA. It's a 40 crores project for both defense and the space applications. So if you could see ARCA, we have special expertise on different areas, and each one is done in a special center where if you walk into any of the center of excellence of powder metallurgy surface, you can see a lot of robots and then pilot facilities where you, as if you are walking into a factory. And then we do all these ones on the big components. If you are doing the surface engineering coding, we do on the turbine blades, we are on the spacecraft, defense components, and then even the industrial automotive components. So it's a powder synthesis, our expertise in surface engineering. We have engineered and functional coatings. And in laser, we have a huge laser machining facility where we also do the additive manufacturing, both E-beam, electron beam, and SLM, that is powder bed process. And we have the ceramic, I already said silicon carbide mirror and low expansion glass. And we also made IR transparent domes at actual sizes, and which are being with the technology transfer to BEL, and BEL make in mass numbers to RCI, who has now export market. Now you know BrahMos is being export to Philippines. So these are all required IR transparent domes. And then fuel cell is the one although now we talk about National Electric Mobility Mission and the National Hydrogen Mission, they are already for the last 20 years. This hydrogen generation PM fuel cell. In fact, we made 20 kilowatt stacks and demonstrated at Neyveli Corporation, where the byproduct of their electrolysis is the hydrogen. And that hydrogen, earlier it was useless because they don't know where to use it. And then that hydrogen we proved that through our PM fuel cell, some of their rules are completed for 1 year, and then that was demonstrated. So now we are working on how to make it compact with engineering designs of your bipolar plate interconnects, membrane assemblies, and then make it more compact so that it can be useful for automotive applications too. And then hydrogen generation is there already because now we are seeing PM based electrolysis so that you can get pure hydrogen oxide without any mixing so that you can separately do it on board. And lithium-ion batteries is our stronghold where we make materials, especially in large scale, which are very key metal like lithium and phosphate. And we also validate when we make the material, we have to validate at the actual device level. So we have a pilot facility where we can make all form factor, like 18, 650, 20 to 750. All these form factors, different sizes of cylindrical sizes, which are relevant to the automotive battery industry. And that's what we demonstrate. And we also have solar energy materials center where we do easy clean coatings for the existing silicon solar cells, and then perovskite solar cells, the next generation, where the challenges are the stability of the materials, and we have to make the prototype devices also, and solar thermal systems where now we have a solar absorber tubes with the concentrated solar parabolic mirrors, and then put the thermic fluid, and then through heat exchanger we generate steam. And this steam we feed into the SOEC, solid oxide electrolysis cell. We are tying up with one of the companies, Pune-based companies, H2E, where they want to have the high temperature electrolysis, which is quite efficient, and the steam is the feed. So it's a green steam solar, which we feed it, and through the solar panels you heat because SOEC and SOS, they work at 750, 800 degrees centigrade. So heat thermally resistive heating, and then run it purely by solar, and that is what is green hydrogen means. And if you see the TRL, if you come to ARCI, our students also, we train them from the beginning that people should understand because all the people should work for our projects, translation projects. So first we teach them that what is TRL, technology readiness level. And then of course for students, if you go up to TRL 3 level, that's they get publications. If something is good, we file patents and then we keep them also as the inventors. But they don't get any kind of monetary benefit because all this money what we get that goes to the ARC. Individuals won't get any money. But our names will be there as the inventors. So if you see the TRL 3 level, which you must be knowing that basic technology research, that is to make the concept at very small level and then proof of concept of the small device level. And that's what TRL 3. But the private sectors, we are also rich, we have a lot of products like you see cell phones. We are already at that level, but not technologically, and they get all the things and then assemble and then make the cell phone. Or you import the cell phone itself. So what? I'll give you an example of battery pack. The battery packs what you use in two-wheelers. 90% of the market in India of the national active mobility is that is only two-wheelers and three-wheelers. And only 10% is the four-wheelers. Right? So in the two-wheelers, to make the battery packs, what they do is the primary main cells they import lithium, nickel, manganese, cobalt, which has got higher energy density because of higher voltage. And then assemble, you have 100 or 150 cells in series parallel combinations to get 48 volts or 24 volts battery pack to drive the motor. Then what happens is you could do all that and then put into the market. And then you must have seen last 1 year back, there are so many scooters they are getting fires, especially in the summer. Because what happens is you don't have the standard cells. The cells are not following any standards. Although you have BA standards, and then they are not following because all these small companies they import them, and then anyone who knows little bit of electricity, they put serial parallel combinations without any thermal management, without any proper battery management system. Because it has to control like in cell phone. The moment it comes to 100%, it cuts off the power to that one. Actually, it's not 100%. At 80% itself, it stops, but it shows as 100% because the lithium-ion battery cell cannot be charged to 100%. So how to fill this gap? If you don't fill the gap, and we keep getting on, in fact, the electric vehicle sales have gone up for some time, and after the scooters are getting fired, and then there's a huge dip in that. And so people don't know what to do, and then you cannot make this. So far, there is not a single company who makes the lithium-ion battery cell. And if you forget, I talked about the battery cell for the electric vehicle. And for cell phone, we have no cells made in India. And then I think 80% of people of 1.4 billion use the cell phone, but still. So indigenization cell technology is not there because we always end up at PRL 3 level and then forget. I don't blame, but there should be people, there should be institutes like R&D institute, if not the academic institute like you, and they have to take care of it. That's what ARCA does. But just one ARCA doesn't help. So ARCA does that, try to do the filling of the gap between this and this. And then I give the example is battery what we have done. And these are the battery files what happened. In fact, this is all because of nickel, lithium, nickel, manganese, cobalt oxide, layered oxides. And then when the temperature shoots up, even one hot spot, one bad damaged cells, which because when you import cells, in battery process you have to make the cell and formate. Means slowly you have to charge, discharge for 1 week or so, so that any gases which are coming because of moisture and they have to be vent out, and then you have to seal it. So that you, because everything involves cost. The Chinese company, in China, if you go, you can have the best quality cells and very least quality cells. So if you want to buy a scooter, it's आम आदमी का है, then कितना देता है? Then you compromise on the cells what you get at low cost. So what happens is the solid oxide, the SCI, solid oxide interface, the anode, which is protecting the carbon, it breaks when the temperature is shooting up, and then slowly the carbon start reacting, and your electrolytes start decomposing when the over voltage goes up, and when the temperature goes around 100 or 120 or 170, then your layered oxide start giving away, it decomposes, and then oxygen adds to the fire, and then it's not one cell will start, but you cannot pull down the fire also because the 4th cell or 10th cell will start up sometime. That's why it's very difficult to stop the fire also. And second problem is that once it explodes, you have lithium ion, lithium cathode, LiPF6, and with argon liquid CC and DEC, then what happens is fluorine start coming, and it is also poisonous. In fact, in Hyderabad, not because of the fire of the scooter, and scooter got fired in the basement, and then the restaurant, in the hotel, it's not just a hotel, there is no lift. So people started climbing down, and this fume slowly, and 9 people died just because of the fumes alone, not because of the fire. So, and people don't know, people are not educated. In our apartments, we have gated there. Some people take their scooter to 9th floor to charge in the hall, because you can just plug into them. These are all dangerous. What we did is Ministry of Roads and Highways. They asked me. I was chairing a committee where we have to give the amendments to the AI 156, which is standard. So how to stop? If you cannot define new standards, at least you amend some of the standards where it can be stopped. So we gave some strict. For example, I'll give 60 degrees centigrade. The moment the patch reaches, you should have a sensor. Then you should give an alarm so that at least you leave the sport and then save his life. And then if one parallel line of this one cell in the parallel string, if that goes bad, and they should cut the power off. So some of the things, some 5 times we gave, and then now that was amended and then made compulsory for the companies, so that last March onwards there are no scooter files because they have to have this mandate. So these are all happening, and then I don't want to show that because for the school people I show what is a nano at all. But nano is very good once you use a nano mission and all, especially for the during processing or time. But already that is already saturated. Many of the materials which require nano size is already established. For example, lithium iron phosphate, unless it is nano, it doesn't work. So before going that, I'll give 2 examples where we translated from the fundamental to the product. So one of them is nano silver, and then there's no big rocket science. That one, you know that the size quantization effect and then the surface class model. You can see different colors based on the size we make nanoparticle. But when we want to translate it and then take it to a company, he's the CEO of Brazil Chemicals, Bangalore company, and he wanted 15 liters per batch as a scale. And we had to work with some of the companies of reactor manufacturers, and we demonstrated. Then at this level, we got it qualified for the antibacterial action, and then finally this was transferred to them on a global exclusive licensing. And they have multiple reactors in Bangalore now, and then they do the mass production, supply to this garment manufacturer, Color Plus, now Jockey, Innerwear. All these guys use silver because silver kills bacteria, especially the socks guys who use silver because socks doesn't stick to the bacteria, is killed because bacteria only eats away triglycerides and all the stuff in your sweat, and then it gives a bad smell because formaldehyde and that capture water, all bad smelling at low pH level. So this is done, and the second one is titanium dioxide, which is a photocatalyst. And then titanium dioxide, when it is anodized form of nanocrystal, when it gets excited with the UV part of sunlight, and then you have electron holes are very strong oxidants, so they can break the organic matter on par with the hydroxyl radical capacity they have, you see on the electrochemical scale. And that's are well-known signs. So we make the titanium dioxide nanoparticle on large scale, and then we do the testing on actual bad-smelling gases, what comes out of the used garments, and then some of the dirt materials also we have done, and some of the gases which are bad smelling, and finally we validated with micro GC, and then we transferred it up, and we scaled it up again like this, and transferred technology. Now this company gives to the some of the garment manufacturers like Flying Machine and the Splash. So jeans pants are coated with the nano titanium dioxide, and titanium dioxide, when you have small stains on that, and it decomposes the stains what are sitting, and then it gets self clean. So you better have two pants of two colors so that people know that you are changing the pants, and then use this today's pant in sunlight tomorrow, and then by tomorrow evening the first one is dry clean. So we thought it will change the world, and then we get millions of rupees and all, but it didn't happen. But we got sufficient money. What we have? Why? Because you may think something big, because I got 1.4 billion people. If 50% of people don't need washing machine, detergent, and all. But people, even I also wanted to wash my jeans pant. And like your cell phone. Cell phone, every 6 months, everybody will want to change cell phone. Your cell phone will work for 10 years. So people want that. So you have to imagine when you start your technology, what kind of impact it will have on the. But still, we got, and in 7 years, we got all the money, both no transfer fee and the royalty, and then it is a success story. This, all this diesel 30% efficiency, and then emission, which has got CO2, CO, and then a lot of carbon particles decorated with, modified with unbound hydrocarbons, and because of small size, they flow long distances, and then from the toxicology point of view, inhalation toxin is the worst toxicity, and then this has to come out. So that's why electric vehicles have come. You can see the COVID-19 time. When you have COVID-19, before pre-COVID-19, this is the India Gate photo, and then during the lockdown, this is the situation. So people predict that if you have electric vehicles, this is the situation. What you can see, even the normal life without any lockdown. So we have a lot of brands which are already there in the market, both hybrid and then pure electric vehicles. But unfortunately, as I said, and most of the batteries and cells, everything is imported. And lithium itself is, now we say that lithium is there in Jammu and Kashmir and all, but it's not the lithium, it is in the hard rock, and then extraction itself takes a long time. Now in IIT we are working on forming groups, extraction metallurgy groups, so that we can get the lithium out. And IMM Bhubaneswar, they are also already working on lithium extraction, but this takes another 10 years. So until that time, we have to depend on imports. So now what is the situation in lithium batteries is like, if you want to buy biryani, if you want to make biryani, and what you are doing is you are importing the cooker and importing the basmati rice and make the biryani. Better you import the biryani. I am giving a scenario that you import the raw material for the battery. Now Amar Raja is excited, they want to set up the battery plant. And the equipment for the battery plant has to be imported because no one makes there is no manufacturing of these plants in India. Right? So any big company, they have to import the plant, which is the capex of the plant, and which is quite expensive. And the raw material also has to be imported. Your lithium carbonate, which is the lithium material, remaining of course iron and all plenty need. So this is the supply chain is a big problem. So what is required is now at least one part you make it in the basmati rice part. If you make in India, then at least you still have time to do this with the manufacturing of the equipment, which we are also putting proposal with some company, right? So that's what we did. So lithium iron phosphate, which is a key material, unlike lithium nickel manganese cobalt oxide, lithium iron phosphate being a phosphate, the oxide evolution point for this is above 405 degrees Celsius. Even your battery gets heated up, it doesn't give the oxygen, and the fire safety is much better. It's called, that's why it's called LFP, is a tropical battery material. Even Tesla when they want to set up the plants in India or China, which are tropical countries, they want to use LFP. LFP is picking up so fast, but the unfortunate thing is we don't have technology in the country. So what we did is we wanted to focus this material, lithium iron phosphate, which has got only 3.2 volts compared to lithium nickel manganese oxide and all, which are high voltage. But the electrolyte what you use in the battery has got an electrochemical potential window, which is almost 4 volts. And if you go beyond that one, you start decomposing. So the material what we prefer, that's the reason it's preferred. If you go to the upper, you are already in the red line. And the graphite is also in the red line, but graphite is protected by solid electrolyte interface, which is the protective layer. When the graphite in the first use cycle reacts with electrolyte, it forms some of the lithium carbonate kind of material, which is called SEA, and it protects. But if the battery starts getting heated up, that SEA goes away and it becomes reactive, and that makes the battery fragile. So now we choose this, and there is another material called lithium titanate, which is a very high robust material for all temperatures, and then is a very fast charging, but is expensive than graphite. For some of the applications like regenerative braking or some of the drone applications now we are working, because drones, when they take horizontally high, you need high power. For high power, that means you have to deliver current in very fast, that's called power. So high power, you need to have lithium titanate, although its voltage is only around 2 volts. So we're working on this and these two materials. We scaled up to a level where we have gone up to the kilogram level. I will show you in the next few slides. But what is key in the process? Lithium iron phosphate is not a new material. If you take lithium carbonate and iron oxide and then dihydrogen ammonium phosphate, you can make LFP. Anyone can make. But what is important is lithium iron phosphate is not electrically conducting, and then it cannot be used as electrode unless you have a carbon coating on that one, which is a current collection. So you have to have carbon coating in such a way that it should be a uniform carbon coating, but as minimum as possible, because it will be a dead weight for the electrode, right? So, and it also has to be very small in size, because when you charge this cell for high power, it should be small in size in nanocells, so that its diffusion length will be, you cannot change the diffusion coefficient, but you can change the diffusion length by reducing size. So now I want to have in large scale the nanoparticle coated with the bare minimum carbon, but it should have the conductivity to collect the current and give to the current collector. So this is what is the process what we optimize. And then initially we have two-step process. We made lithium iron phosphate by flame spray pyrolysis in the kilogram level, and we started coating carbon in the second step, and it's quite successful. It's on par with global benchmark products. But unfortunate thing is, it's too expensive and no one was ready to come. We spent almost 5 years, but no one was ready to take the technology. Then we started solid state process where in one step we have carbon coated material, and it took another 2-3 years to make that, and now we are ready. So this, and I already told you that the size of nano will help by decreasing the diffusion length, so your charge and discharge become very fast. So initially we have the machines is a high energy milling, where you have to take all the raw materials, lithium carbonate and iron oxalate, and some of the additives to have a robust carbon, which is the key process what we file patent, and dihydrogen ammonium phosphate. So these things you can mix it, atomic scale mixing, that means you have to do real mixing so that your reaction is much homogeneous, you don't have any impurity phase in your LFP. That's possible, but the cost of the equipment, I said capex, cooker cost, and it's 100 lakhs, 1 crore just to make 1 kg material. And we performed and we did excellent results. We got on par with the imported one, but the unfortunate thing is how many machines you will buy, and no company will do that. We failed the first time in two-step process, and this is another failure. But still, we have to do that. So what we did is we started designing a treater by ourselves with a fabricator, and then we started manipulating and optimizing the parameters, and finally we have a product of this which is just for 3 lakhs. And you can see they're on par with each other, both in terms of C rate as well as the specific energy. So that's what is the easy adoption of the technology. Because unless you make, now I can do these ones on 20 kg level, because there is just indigenizing that data, right? You go to the fabricator and ask them and give a design, and then we can do that. In fact, we did it. So now at this level, we transfer the technology to this company. It's the Altman, it's a Hyderabad-based company, and this is the principal scientific advisor to state government. and this is our team. So what they want, there are two kinds of rights we give. One is non-exclusive licensing, which means we can give to multiple companies, because this being a priority material, and then the need for lithium iron phosphate in up to National Electric Mobility Mission says that by 2030, 30% of your vehicles should be electric. If that is a target to be met, then the material what is expected is 250,000 kgs of 250,000 tons of lithium titanate is required if lithium iron phosphate if all these vehicles have to use it. So that is an exaggerated number, but you can say 50% also, not a single company can make it. So the response is so huge, but we need to have this technology ready within the country. And also you have the use export market, because when we wanted our pilot facility to use 100 kg of lithium iron phosphate to import from China, no one is ready to supply, because there is not enough material to supply, because globally it's a very demanding material. Then we went to Taiwan and then we got it, and then they could supply some 10 kgs, but that is the problem. Now we have our own material. That's the first thing. And the second thing is, when before they pay the check of 40 lakhs, we thought that we'll give to 6 people of 40 lakhs. And before we go, they wanted a third party validation. We went to IIT Mumbai, they have a pilot facility, and we took our material and then did all these coatings and all, and we modified the tap density and all, so that you have enough material in the cell so that your energy densities are par with any kind of things what you import. So this is what where the commercial and then the indigenous were very close at very low cost, and then these cells are made and this data was shared. Then they wanted, because all these companies are startup companies, they don't lithium battery technologies are not known in India. People may spend money, Adani or Reliance and all, but for them to run the show, they need to have the manpower, they need to have the trained people. So this is not there. So what they did is they wanted to put a pilot facility on our campus, and then this is the pilot facility. You can see all these machines are indigenized. Like I said, we have made the 8 liters, now it's the 20 cases of the 8 liters, and then all of them, they're all indigenized equipment. And then they can make 100 cases per day production facility on our campus. And then we take rent, we handhold with them until we train their people, both on the process and also the calculation. And you can see Saraswati is Nitya, and then Parmabhushan was Anil Kapotka. And then we have these products, and then already now we are making 50 kg batches, and those are already tested and validated by third party as well as ARC, which is on par with the global product. So now Telangana government has given land next to Amarraja land for setting up a huge plant, and then Gujarat they got some investments of 300 crores to set up a mega plant. All these will start from 2 or 3 failures what we did. So the translation value of that is that you start some experiments of the new process, and then you have to have, without patenting, no one will take technology. So what we did is we filed Indian patent, and they want, because they know that they have went all the countries these days. These days I got access to Bolivia, and South American countries I got a lot of lithium minerals, but it is very low cost because they are all poor countries. So these people have got access to some of the mines of lithium carbonate, which is required, because tons and tons of lithium carbonate is required. So now they get that one, and then that material also we validated that with that raw material we can still have the same kind of capacity and then see rate what we are benchmarking with any imported one. So now they are ready with a big plant in the next 2 years. That plant will come. So now what I want to say is, we filed the Indian patent. We took PCT, that is PCT document. Sanjay, what is PCT?
Patent Cooperation Treaty.
Treaty. That's a international where you have to do that so that for 1 year you are protected in any country you can file. So then what these guys they want, since they have an export market, like we could not import, other countries also they cannot import, so we want to export, because that is one what they see a lot of benefits. So they want to file in 4 or 5 countries, which is almost 25 lakhs. We said that we are the inventors, but you put money to file there, and they filed. So we got also, some of them got granted, and some of them still were waiting. So this is what the success story of one material starting 10 years ago from few failures, not on the material property wise, but on the process and the cost and the production. Those are the hurdles we crossed. There's the value of that, and today we are there. And for the global Indian non-exclusive, we have 40 lakhs, and for global exclusive rights because they put money on our patents of 25 lakhs, and for them to have the global licensing other than India, 3.5 crores they paid. They already paid the checks. So now, once this factory starts, their suppliers to the Amaraja, they also have some other companies abroad. They want to have access to this company to have the supply chain. So this is a story. I think so. I don't know how many people know because many are physics people, so you know what the capacitor and the battery. And supercapacitor is the one where you can just dump the currents. This is a high power. So these are all very well known. So what we did is uh, uh, you should have a very high surface area material which are current collectors. In both cases, you cannot have low surface area metallic which will be expensive. So it's actuated carbon. And in Maxwell, which is a US-based monopoly company, they use actuated carbon from the coconut shell, and then they get it from the Kurare, one Japanese company. And Japanese company makes this actuated carbon from the coconut shell, which they get from the Asian countries because we have a lot of, including India, Philippines, and all. Right. So that is well known. They have a lot of patents. But then can we have the carbon from other sources? We tried, and both electrodes are carbon, and it's nothing to do with the redox or the bulk property. It's only surface charge, and the ions of opposite will go into the opposite electrodes, and then they sit down at one. When you discharge, they quickly. So in seconds you can charge and discharge, but energy density is poor. And then you have a battery vehicle which can run 100 kilometers. If you use supercab, it may go up to 5 kilometers or so, it stops. But you can go like a race car. In some of the race cars in Formula, they use supercapacitor because the distance is not so much, but they have to go very fast. Right? And in recent rate, the braking also used because when a heavy vehicle stops with sudden brake, the energy should be absorbed so fast to charge the battery, and battery cannot do, and it's the supercab. So some of the vehicles, they already use supercab. In China, they use supercab powered buses for the public transport because by the time the bus comes and stops at the station, bus stop, by the time people go and people come out, you get charged and then that keeps going. So these are already demo buses are there. So with this idea, can we do this? Of course, it may take another time. Already battery technology itself is taking a lot of time, and supercap technology may take some more time, but we are ready with that. So initially we start we'll do with the jute derived carbon, and I think a lot of jute sticks, it is a useless material except for the firewood kind of application, and even in coastal area where my childhood we used to use this. But it is a cellular kind of structure where if you convert it into carbon, activated carbon, you can have a graphene kind of structure. You can see the 2D band shooting up. It's not there, but it's like this with huge surface area. And the commercial, when I say commercial, it is actually Kurare material what is being used by Maxwell, and then we compare it. It's excellent, but the yield is very poor. But with these properties, when we showed to HPCL, and HPCL got interested because they have petroleum coke, which is a used waste. Also, there was a ban after the present government took over. They banned import of the petroleum coke because earlier the advanced countries used to dump petroleum coke in India, and for us it's a cheap energy source. The cement and oil industry, they use petroleum coke as the energy sources, but it has 5% of sulfur, which gives sulfur dioxide, which is very, very bad for the environment. So there is a ban on that, but in spite of that, in the country, India itself, oil refineries produce millions of tons of petroleum coke, and then that's still being used as a fire source. So HPCL wanted their petroleum coke, which is very rich in carbon. If you convert bio or coconut, it's only 30-40%. Here, more than 80% is the carbon. So what we did is we converted petroleum coke, and we did some kind of multiple step activation, and then we made it, and then we are on again par with the Kurare's carbon, which is a Maxwell material, and then we have they funded us a few crores to establish a pilot facility, and then we made the devices on par with even the size and the capacity and its energy density on par with Maxwell. You can see Maxwell and us, and this is a pilot facility what we have, and some of the devices actually machines what we need, and we got it fabricated within the country, so that slowly we want to make one by one indigenized, so that in the process line also we want to indigenize. Now we have big proposals we're putting to the government that at least one pilot facility of the making a cooker part, I say. So the facility will be made totally with the Indian components, so that otherwise all these are imported from China. So now we have the super cap for the first time with 1200 farad capacity on par with Maxwell. ISRO and CMET and all, some of the research labs, they make super cap, but up to 500 farad, not above 500 farad. If you want for any electric mobility kind of situation, you need to have 1000 farad for above. So now, why they cannot make 1000 farad is because you need to have this kind of facility where the ends of this current collectors, the anode cathode, they should be flattened here, so that the electron what is generated once they straight away come to the terminals. In normal capacitors, what others do is you put a strip and then you put nickel tabs at a distance, so that when you draw very high currents, the electron has to go to very far distance and then it just dies or it gets heated up. So this is a problem where people cannot make, and we are successful. And this technology now we want to use for the batteries also. And now recently we filed a patent for super battery, where both energy density and then power density both are balancing. And then that we are not showing because it is in the pilot patent process going on. So with the super caps, what we made, I cannot demonstrate a bus, but with our little money, we demonstrated a bicycle where it is on ASI campus. We run this bicycle for a few kilometers and then test it and then collect the data. And now we want to keep this in a hybrid mode with the lead acid battery vehicles. If you go to Banaras or in UP and all, you can see that a lot of auto rickshaws are electric rickshaws only. They are not lithium-ion based, they are all lead acid battery. Because lead acid is a mature technology within the country with more than 99% is the recyclability of lead is there. See, the technology will never die, but the problem is that whenever you have the roads with up and down and then speed breakers and all, many times stop, it needs to draw current and then that will kill the cell. So it's not 2 or 3 years, you'll get only 6 months is the lifetime of lead acid battery. But people still want to go because it's very cheap, unlike lithium-ion. So what we did is we connect these ones and to the lead acid battery auto rickshaws and show that its life is increased, because whenever there is a burst of power is required, on, off, or then stop, and your electronic circuit take this load onto the super cap, and whenever you are on the straight roads, it takes back onto lead acid battery. So that is demonstrated, and we are working with some of the auto rickshaw companies whether we can integrate our super caps with them so that their lifetime will be increased. And some of them we are working with the drone companies and all. This I was showing. Value of death also shows that when you want to gain something, what you have to lose. So a lot of hair is lost during the course. So but कुछ पाने के लिए for students when I use this photo. So we have a lot of students, engineers, scientists, technical staff, all these, a lot of students. We have 50 students who work for PhD, and we cannot be like, because ours we cannot do PhD degree, so IITs and NITs we got, and then a lot of fundamental knowledge what is coming off professors like you, and that is being utilized in a translation. I want to tell you one thing. You take LFP itself. LFP is not a rocket science, because you know lithium iron phosphate, how to make any solid state reactor. But the process what we have to make, that is should be identified. That there 90% of the technology you can always reverse engineer and do that, and you can reach up to 90%. But when you go from 90, 95, 98, 99, then you have to work logarithmically 10 times to get even 1% more. That part, the last mile of the technology can be filled only when you have the lot of fundamental stuff. So one kind of group like ARCI or one kind of only SLPOs, they cannot do unless they join hands, because that last mile has to be finished. Otherwise, you can never compete with the global product, and then this technology will still be there, and then after some time you forget about it. So the comfort zone, out of the comfort zone, people have to come from the both sides and work together to fill the last mile, so that it will be globally accessible products. That's why I am here, because I know and we have to take some of the help of your computational experts also, so that our number of students will come out. So we'll access some of the visits. That's the purpose of my visit. Even now I'm going to be visit advice to IIT, so that we can also couple with some of the IIT groups also. So thank you so much for your attention, and now open for discussion.
Thank you, Professor Rao, for the same. So some questions maybe.
Yeah, so
Thank you so much for giving a good angle to all the research what we do in the lab. And the question is like the last part of your talk, what you mentioned that clubbing the supercapacitor
yeah, hybrid.
lead acid, you could demonstrate that. But it has been suggested and it has been technically proved also that the same thing happens with the lithium-ion batteries, or same thing happens with the batteries what you showed with the supercapacitor. That is kind of the future. Is there anything going on in
No,
that direction?
see, because if I understand you correctly, lithium-ion battery itself works like a hybrid mode because it can take a lot of its power density also very high if you compare with lead acid battery. So it doesn't require the supercapacitors at all, especially for the application like scooters and three-wheelers where they don't go exceed 50 or 60 kilometers per hour.
Yeah, the only question which was being asked and people are trying to understand it now, like reduce the time of the charging. For example, supercapacitor may charge quickly and then the
But it
power.
doesn't work. It doesn't have enough energy. Now, what we did is with the flattening of the ones what we use for supercap, even Tesla has bought Maxwell because the only technology of the flattening of that one where you don't need tabs, tabless welding it's called, and that they are using in the battery. So we started doing that because we have developed the tabless technology. So now we are working the tablets on the battery itself. So now lithium titanate, although you are compromising a little bit on voltage, now we have a LTO LRP technology battery with a tablet, and it is almost like a super cap with not compromising on the energy density. It is in between the super cap and which is one now we are actually demonstrating on the roads.
Yeah, and the second question, yeah, okay. How much industry is really concerned about the like bulk scale synthesis? Can you just comment on that? Because some of the materials we synthesize maybe on the gram level, but industry might need on the kilogram level.
That's what I said. No, when we made up to 20 kgs, we could make it by ourselves. But because what we did 1 week, we took rent one of the companies, powder metallurgy company, their machine. That 1 week you stop, and then we give money. They said we don't want money. We said 5% of our no money we give it to you, provided you do this. So 1 week, like almost 6 months, 1 week, like 2 or 5. We use it, we make 20 kgs of batches in a pressure pipe furnace. And then those materials we tested, and this data with the IIT Mumbai, well, we showed to them. And they took the material and gave to some Warwick, UK or somewhere, and then they got qualified. Then only they gave the check.
Okay.
So this is very important. If you don't do at that scale, they don't even care.
Okay, thank you.
And the royalty what we are going to now get, if you think that even 10% of what their projection by 2030, that royalty runs into tens of crores for years itself, if they show the correct accounts.
So the lithium titanate, of course, is good for one kind of application,
Yeah.
and lithium iron phosphate for another kind of application. So is there some attempt to make some alloying of the two, and is that a still phase?
But
Because what you were saying is more like a hybrid, where you use this material and that material.
yeah, no. In this particular case, I'm sorry, I go very fast. That is one of the. So what I did is. Yeah. So cathode and anode, instead of graphite anode, we are using lithium nitride. Still, this is the anode and this is the cathode, and this the difference in this EMF is the 2 volts. Yeah. So you still need both of the materials. So you can say that LTO can be mixed with graphite and then do the alloying. In fact, LTO we also put little bit of carbon when is required to increase further.
So here, for example, really the kind of granularity,
Yeah.
everything that matters.
It matters a lot because
The
you have
morphology matters a lot.
here what is required, you need to have nanoparticle, but the tap density should be very high. That means you should be able to. So what we do, we granulate them. That means billions of particles we make it like a glass. Actual particles they are micron size only, but each micron size particle contains hundreds of nanoparticles, thousands of nanoparticles, so that's the Gibbs gradient.
Yeah, maybe I didn't get it very well because you showed this coating of the carbon.
Yeah,
I think later on in some slide. So was
Yeah,
it for the
this one.
okay, but this coating of the carbon, there it was actually this coating was on the cathode.
on the cathode,
Ah.
which has no role, actually this is detrimental.
Yes.
But you need to have carbon to collect the current because the conducting element is not conducting.
Right.
But if you have more carbon, then that's a waste only, that way. So you should have a bare minimum carbon
A balance
with good
of-
conductivity,
Yeah.
but it should be a drop. So that's what we optimize.
But you never used it at the anode side.
Well, because anode is already is conducting.
No. By mixing some form of graphite
Yeah.
with lithium titanate.
Yeah, but lithium titanate, which is anode, we did it because we
You
did
did it with some carbon.
no, carbon coating only. There also
I see.
we did it because lithium titanate is the main one. What it gives a high power. But little bit of carbon, because lithium titanate also semiconductor. Little bit of carbon will enhance its conductor. So there, it's the hybrid mode is work. But you should not use for cathode carbon, which is written. That's why that bare minimum carbon is required. But without carbon, it doesn't work.
Nice. So the other question is how sure you are of the oxygen stoichiometry, because that seems to be a very
Yeah, but here, since it's not a layered material, phosphate,
yeah.
arsenopene usually is not a problem because phosphate will come, yeah. But if you have layered materials like LiCOO2, then there is always a problem of oxygen.
Because I had that.
Yeah,
in mind.
yeah. But in phosphate, there's not. That's the advantage of phosphate.
Yep.
And it has high temperature resistance. That's why it's called tropical cathode.
Sure. Thank you.
So it's clear. That is not. Okay.
Okay, so.
Is there no more
So
questions?
there is no more question. Let's thank Dr. Tata for answering.
Thank you so much.
We have to answer. Thank you.
But there is some of the industrial matters there.
Yes, sir, yes.